Hi, welcome to another 4AC video. This round we look at 4AC tutorial topic 4, question 7. The question reads, a 230 volt 50 Hz AC source supplies two loads. Load 1 draws 5 kilowatt at a power factor of 0.75 lagging, means that it's an inductive load. And load 2 is a 10 kVA load at 0.65 lagging as well. So in other words, two inductive loads. Now what are we required to find? First, we want to find the real power and the reactive power for each of the loads. And then we want to find the total apparent power supplied by the source. Next, we want to determine the capacitive element required so that we raise the power factor to unity. In other words, we compensate for the reactive power. And finally, we want to determine the change in supply current from the uncompensated to the compensated system. Alright, let's see how we can answer this question. Well, to answer this question, what I have done is to draw a diagram showing the two load 1 and load 2, and the AC supply. Alright, then I would develop a table like this so that I can just directly compute what are the various real power and the reactive power of each load. Now, in load 1, we are given the real power as 5 kilowatts, so I will just write here 5 kilowatts. Now, for the reactive power, I would need to know based from the information given here, I can derive the apparent power and the reactive power. So for load 1, I know the power factor is 0.75, which means the cost of the angle is 0.75, or the angle is 41.41 degrees. Hence, the sine of the angle, sine theta, will be 0.661. So to calculate Q, I can make use of the right angle triangle. I know Q is here, P is here, and this is 41.41. Q will be just P, the tangent of 41.41 degrees. In other words, I can just say P tangent 41.41 degrees. That gives me 4.41 kV. R reactive. Okay. And to calculate Q, I can make use of the fact that P is to calculate S. Sorry, P is S cosine theta for the power factor. Therefore, S is just P divided by cosine theta. So this is just P divided by cosine theta or the power factor. So that's 5 kilowatt divided by 0.75. That gives me 6.67 kVA. Alright, that's for load 1. Similarly, for load 2, I can use the same approach, where the 10 kVA is the apparent power. So here is 10 kVA. So P is just the apparent power times the power factor. So it's 10 times 0.65. So it's 6.5 kilowatt. If I were to draw the triangle again for this case, triangle P is here, Q is here, S is here, right? I know S, I know P, I want to find Q. So what do? I can find the angle, or in this case, I can do a subtraction. So Q squared is equals to square root of S squared minus P squared. That gives me 10 squared. 10 squared minus 6.5 squared. So that will give me a Q value of about 7.6 kVAR. Right, so that's the individual real power for each load, the individual reactive power. Now both reactive power are inductive, right, because both are lagging power factor. So both are positive J, so I can actually sum them up and then determine the overall apparent power. So here is 5, here is 6.5, so it's 11.5 kilowatt. Here is 1112.01 kVAR. And to find the overall apparent power, we will use square root of P square, the overall P square here, PT, QT is this one, right? Plus QT square will be equals to 11.5 square plus 12.01 square, the whole thing square root. That will give me a value of 16.63 kVA, the total apparent power for this circuit. Okay, and what is the overall power factor? The overall power factor can be given as PT over ST. So PT is 11.5, ST is 16.63. So the overall power factor is 0.692, lagging because of the inductive load. So I have the power factor, I have the original circuit's real power, reactive power, and the apparent power. Alright, so that's the first part of the question. Now the second part of the question asks me, what can I do to correct the power factor so that it has unity power factor? In other words, I must try to introduce a capacitor that will compensate for this. That means the capacitance I introduce, reactive power, must be the same as the QT. That's 12.01 kVAR. Now, we know that we can use this calculation. In other words, I want to introduce a capacitor here. This capacitor will give me this reactive power to compensate for the current reactive power. So that can be calculated from V squared upon XC. Therefore, XC must be equals to V squared is 230 volt, 230 squared divided by 12.01 kVAR. So that means I need to introduce a capacitor that can give me 4.405 ohm. Okay. But we also know that the reactance of a capacitor can be calculated using this formula, 1 upon 2 pi Fc. Therefore, the capacitance I need to introduce must be equals to 1 over 2 pi 50 Hertz, and this ohms 4.405 ohm. That gives me a capacitance of 722.6 microfarad. That is the capacitance I must introduce here, so that the power factor is corrected to unity, that means Fp equals to 1. Right? Now, the final part is determining the difference in the current. The original current I1 original is just the original total apparent power, which is S divided by the voltage, which is 16.63 kVA divided by 230 volt. That gives me a current of 72.26 ampere per phase. Right? Now with the new compensated power factor current, the total apparent power would have dropped. Right, this is 0 now, so drop to 11.5 kVA divided by 230 volt. That gives me the new current of about 50 ampere. Therefore, improvement in the current in the circuit is equals to 72.26 minus 50. That's 22.26 ampere. So by just introducing a capacitor, I actually reduce the overall current flowing in here by about 20 over volts, and that's very useful in circuit cable sizing and heat loss and so on in the circuit. Alright, so that's all for this question, and I hope you learned something from the whole answer.